Hello there. So in this lesson, we're going to look a little more closely at power. Now that we've learned about current and voltage, there's an interesting connection between the two. We've already learned a little bit about power because it related to how quickly the devices around our home use up energy. So today we're going to look at how the power is related to current and voltage. So recall that power is the amount of energy being converted over time. And so the faster that you convert your energy, the more powerful the device will be. So all your loads, they change electrical potential energy, that's stored energy, into other forms like heat in the toaster and light in the light bulbs and sound in the piano and motion in the fan, right? So since energy can't be created or destroyed, this conversion is what we measure with power. So here's a whole bunch of the loads that we mentioned there earlier. The other thing to understand is that generators do the opposite. So they'll take some external form of energy, in this case, the movement of my hand, and turn that into electricity, right? And so since that's another conversion, we're going from motion here to electrical potential. This is also a power situation where there's going to be a rate at which that conversion can take place. So you can use power in either place. You can use it for loads and you can use it for generators. Okay, so recall that power is measured in watts. Remember, after the Scottish inventor guy, a steam engine. And we measure energy in joules and time in seconds. And so there's that same relationship that we already spent a little time looking at, being able to determine how much energy you get per second. So the next step is to connect that to the current and the voltage that we just learned about. So here we go. The relationship between power and current and voltage is you just multiply them, right? So the power of a given device, like a load, you can find that by multiplying the current times the voltage. If you want to make a triangle out of that, power is current times the voltage. Now, in order to show that the two measurements of power are the same, we can do a little neat math. You generally don't have to do this in a test situation, but I think just for your own understanding of things, it warrants having a look at. So this was the other relationship for power, right? Power is energy divided by time, but power is also current times voltage. So we know that power is current times the voltage. We can substitute in what we already learned about current and voltage, right? So current is the charge divided by the time, and the voltage is the energy divided by the charge. And so if you multiply those two, Q times E and T times Q, you see that the Q's cancel out, right? Q divided by Q is just 1, right? And you're left with energy divided by time, right? From the same calculation, right? So there's a neat connection between both of those that will help you to deduce the power of a given device using either the energy and the time, or you can use the current and the voltage. So here are a couple that use current and voltage. So we got a current of 0.5 amp, and we got a potential difference of 6 volts. What is the power? So power equals I times V, and you can put in 0.5 amps for the current, and you can put in 6.0 volts for the voltage. And so half times 6 is 3, and since it's power we're looking at, it's 3 watts. That tells you how fast the energy is being used. Alrighty, using our relationship, if you want to use the algebra to figure it out, if you want to use your triangle, if we were looking for the potential difference this time, and we're given the current and we're given the power. So we want to find this guy, right? So V equals P divided by I, and we've got 40 watts divided by 0.25 amps. And if we divide those, it's going to be 160 volts. So that's quite a bit of voltage in the toaster. All right, take care.